Hello.
Hello.
I took my webcam down for a couple weeks. Let me get it back.
Okay, I'm fixing
Yeah, the link was a little wonky, but I got it to work.
the web server because it has a malformed URL.
Yeah, I changed 1003 to 1330 and everything was good after that.
I'm about to completely fix it.
Also, unless there's a new update to the file at that location, there's an error somewhere down in there, but I'll explain it when I get to it. It's not a big deal. Hope everybody's ready for statistics.
That should fix it. Okay, it should be fixed.
All right, let me check it out.
The recorder's running.
Sorry, trying to get my webcam on. I had it unplugged. And you know how friendly Windows is with drivers.
And
I
pass
wouldn't say it's a driver issue. It's just,
homework
just wanted to use OBS.
also fixed. Okay,
There.
the links are fixed. If
Cool.
you're not getting the fixed ones, try refreshing your browser.
Oh, don't want to share. Okay, so let's try.
Hard, that's quite a comment.
All right, let's see. Need to probably refresh. Yep. Is everyone able to see my screen and also hear me? Cool.
You got a yes from Mr. Jackson, so
That's at least one.
that's one.
All right.
If you get a second one and a third one, then by induction, you've got them all.
Hey, I appreciate that.
Okay, I'm gonna keep quiet and just kind of listen in and
Okay. So today's going to be kind of a, I don't want to say it's a theory lab, but as you will see, a lot of what's going on here is going to be, we're going to do some stuff, and then we're going to have to reflect on it. And these questions are a large part of what we're going to be doing. And as you can see, that's going to be what you're doing here too. So let's get to it. So I didn't take a look at the lesson today. I should have, but I'm assuming that you at least have heard the term hypothesis testing. And the lab is getting towards that. So what is hypothesis testing? Well, it's what you would expect. You have a hypothesis, which this is definitely not a formal definition, it's just off the top of my head. This is a statement that you are speculating is true. And what you would like to do is have a test that says, with some level of confidence, we fail to reject that our hypothesis is wrong. That's basically how it works. It's called the null hypothesis, but I'm not sure if you got to that or not. All right, so we have our packages that we are going to be using. So NumPy, pandas, all the fun stuff. I've already ran these, and there's not much fancy about actually running them. So I'm not going to just rerun them and clear them and rerun them. So we're going to make a request to get our data, and our data is going to be a CSV that looks like this. A bunch of stuff. And there's some more stuff we can do. Generally, when I have a data frame, I want to run the describe and see what it looks like. So I'm going to do that. So we get our CSV from the request, open it up, make a data frame out of it. We call it my data. And I'm going to say, I'm going to run this. Okay, so what are we looking at? We got 100 of each. They appear to be some floating points. Mean of set 1 is 48.5, 508 on set 2. We've got a standard deviation of 15 over here and 46 over here, which may be proportional. This is about 10 times the size of this. No, we'll see. So question 1, what are the name of the two series in my data? No module named requests. You have to, that's weird. That's very weird. Requests is a package that comes with a default installation of Python. It's not a funky one that you have to go actually install. So that's really strange. Try restarting Anaconda. Like, okay, good. All right. Oh, yeah, there are two Jacksons. Okay. So question 1, what are the name of the two series in my data? Well, I don't know. Question 1, what kind of thing is my data? What is the data structure of my data? There's a couple ways to find out, or if you already know, you can just say, so what kind of thing is it? Is it a list? It's a data frame. Yes. No, it is not a series. And that's what I am, the reason I'm taking time to go into this. It is definitely not a series. It is a data frame. Why is that important? Well, what makes up a data frame? What kind of thing are the columns in a data frame? Well, just like I said, if you don't know what the type of my data is, you can find that out. I can say print the type of my data. It's data frame. I can also say I want to get the type of one of the columns. Now, how do we get a column in a data frame? Well, we index and we use the actual name of the column. Look at that. We've seen this before. The columns in a data frame are series. Ah, okay. I see. So a column in a data frame in a series. So that leads us to be able to say, what are the names of the two series in my data? Well, I don't know. What the heck is a series? Well, the columns are series. So this is the same question as asking, what are the names of the two columns in our data frame? So what are the two names of the columns? Names of the two columns. Well, it's set 1, set 2. Now, what would happen if I were to change the case of this? Would it work? No, it would not. It would say there's a key error. What's a key error? Well, we're treating our data frame kind of like a dictionary, and we're looking for the key set 1 with lowercase s, and there's no key by that name. Reason that's important, well, obviously it won't work if it's not case sensitive. So the name of, is this code cell? I'll change it. The name of the series are set 1 and set 2. Okay. Describe the two data series, which has a larger mean value and which has a larger variance. Well, my tendency, that could be a normal distribution pun. Ha. My tendency to use the describe method every time I make a data frame looks like it paid off. Since we know that the series are part of the larger data frame, when I ran the describe data frame, I noticed that we get all this fun stuff. So you have all the information you need to do this question. Now, I guess we'll just go into it. So describe the two data series. Someone describe one of them or two of them. I don't know. What would you say a short description of these are? In one sentence. I'm pretty sure I already said one earlier when I did it. Now, which has the larger mean value? Now, this doesn't take much thought. You just have to compare them. Where's the mean? They're right here. Where's the variance? Well, does anybody remember the relationship between the standard deviation and the variance? I keep seeing no at the bottom of the chat because it was the answer to before. Yes, one is the square of the other. So if you know that, you can pretty much answer which has the larger variance. So describe these two data series. That's the last part, question 2. So can somebody describe the two data series? Or if it's easier, just describe the data frame, put it that way. Set is, yes, that is correct. But we're working on describing the two data series. Well, if you're having difficulty with that, let's try this. My list is, let's see. All right, I have a list. Can somebody describe my list, please? It's not a trick question. What are the important parts of my list? 3 data points ranging from 0.01 to 99.9. Yeah, I mean, it's not how I would do it, but it's good enough. Here's what I would say. It's a list of size 3 with floating point numbers. That's what I would say. But I can infer that from your answer. So what's the important parts? Well, it's a list. It has all the same type and the floating points. You went further and said the range. That's cool. And what the most important thing I would say is the how many there are. There's 3. Okay. Well, let's do the same thing with set 1. Can somebody describe set 1 in the same way that Jackson described my list? In fact, you actually can do the same thing. We have the information to do the range. So the important points that Jackson pointed out were the size of the container, what kind of thing is in the container, which is floating point numbers, and the range. So do the same thing with set 1. How many are in there? A float list, 100 members. Yep, good enough for me. Set 1, I would even say the 2 data series are each a series of floating point numbers with 100 members each. So I wouldn't say list. I would say, because a list is an actual type in. I like that I'm talking to an iPad. It's not James. It's James's iPad. It's a sentient artificial intelligence. I wouldn't say list though, because list is a thing in Python. But good enough. Yeah. So describe the 2 data series. Well, there are 2 series of 100 length each, and they're floating points. Which is a larger mean value? We already know that. Which is a larger variance? We already know that. All right. Job's done. Job's done. Okay. So we've got 2 sets of stuff. Let us make a histogram of the 2 data series. Now, what's a histogram? It's that bar plot looking thing that has buckets or bins that you throw stuff into and you can visualize them. Now, what does it look like if there aren't very many bins? Well, looks like this. Not very useful, is it? So let's expand the number of bins. So it's something that is useful. Now, what we have was actually 40, but I'm just showing as the number of bins go up what it kind of looks like. So just based visually on what we're looking at here, would you say that these 2 data series are similar or not? Well, is that the right way to say that? Are they similar? That's what I would say. We got a set in blue, we got a set in orange. Would you say they're similar? Okay, we got 2. Yeah, I would say no. I say their similarities end with the answer to question 2. They both have 100 floats. That's where their similarities end. They don't even intersect. The values in set 2 are much larger than the values in set 1. Moreover, remember how we talked about central tendency? The spike in, where's my this thing? The everything is much more concentrated towards the center than it is here. Even though this looks more like a, yeah, it doesn't look great, but everything is more concentrated towards the center in set 1. So I would say they're not similar. That's what I would say. Okay. So are they similar? So no. How are the series different? Well, I basically just said it all. So I guess since there's not a whole lot more to do, we'll just actually do that. So again, this isn't a trick question, and somebody other than Parth, because Parth is a trooper and is always participating, can somebody describe how these 2 series are different, blue and orange? It's just an English sentence. There's no trick question here. Although I am a fan of trick questions, though I don't particularly view them as trick questions. One is more concentrated. Yeah, okay. They have different means, different distributions, and they don't overlap. Disagree on that one. I would not say they have different distributions. I know what you're trying to say, but you got to be real careful. Because they're both normal. I think we go into a lecture on what the distributions are. Either we haven't got to it yet, or we've decided to skip it. But they're both normal. But I know what you're trying to say. Their distributions are different in the sense that both are normal, but one is more smushed than the other. One is a big standard deviation. Yeah. Yeah, all those answers are fine. Those are good. I wouldn't have even said that Jackson's is wrong when I'm grading it. I would just say that technically you're not correct. And as I am prone to do, I'm going to make a Futurama reference. Technically correct is the best kind of correct. All right, so that's question 3. All right, so now what we're going to do is we're going to generate some more series using the descriptive statistics from set 1 and set 2. Now, as I've warned before, I told you to remember what descriptive statistics are. So somebody tell me, other than Parth, because Parth's a trooper, what is a descriptive statistics? You can explain it or you can give me an example. But what's a descriptive statistic? Various statistics like mean, standard deviation, range. Yep, that is what they are. That's right. And I'll even go so far as to answer the rest of the question. What makes them descriptive? It's because using those things can describe the set just by themselves. I don't need the whole set. I can make something useful just having those. In fact, that's exactly what we're going to do. So I'm going to make a new series from set 1 and a new series from set 2. Now, what the heck am I going to do here? I know they're both normal. Now, you're just going to have to take it on faith that both of these distributions are normal, because I don't have the time to give the theory explanation of when a sample falls under the normal distribution or not. The best one sentence answer I can give you is, does it kind of make a balanced curve? And this one does. Even though the thing is, if I were to if I were to basically zoom in on from 0 to 100, this you'd see that the blue one falls into a normal curve. But that aside, once we have a normal distribution, what I'm going to do is say, all right, I've got my data. But what I want to do instead of actually using the data is I want to randomly pick from that set of data. And what am I going to use? I'm going to use the mean from the data. So I'm not actually going to use the data itself. I'm going to use the mean and I'm going to use the standard deviation. So I've got my data with all the stuff in it. It's actually called my data, but I'm referring to my data, 2 words. I've got all my data in here, blah, 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 blah. I don't actually care about what the numbers are. I care about 2 things. What is the average? What's the mean? And what's the standard deviation? So using these 2 things, it kind of looks like a vehicle now, or a smiley face. Using those 2 things, I'm going to recreate a normal, another set, just like that, using the 2 things I just mentioned. But I'm going to randomly pick them. So I'm going to do that for set 1 using the mean and the standard deviation for set 1. And I'm going to do the same thing for set 2. Now you notice the standard deviation for set 1. I'm sorry. Let's talk about the means first. The means for set this one are smaller than the means for this one. How do I know that? Well, the range of where it goes is less than the range of where this goes. And the standard deviation is different. How can I say that just by looking at it? Well, the visual indicator of standard deviation is how far out does the data vary, because it actually, it's from the variance. So how much does the data vary? You could say that orange varies a lot, even though it's relative, but it varies a lot compared to the blue. So there you go. All right, so let's do that. Put these into a new data frame. I'm going to call it _D. And we're going to make a histogram, same bins as before. So something you'll notice here. Let's see, when I have to actually rerun everything. This, as I said, is random. We just made it up. But so life or death, if you were asked the question, are the blue and the orange from the randomly generated similar to the blue and the orange from our actual collection? What would you say? I'd say yes. Yeah. Now, why is that the case? The short answer is the data we actually collected, is normal, meaning it forms a normal distribution. And the reason it's actually called a normal distribution is exactly what you would expect. We find it all the time. It occurs the most often. Well, I won't say that, but when you go and you collect data about like real life stuff, not theoretical things, when you poll people, this is what you're going to get most of the time. All right, so here's a neat trick. No, it's not spinning. Remember, I made these two new sets randomly. I'm going to make them again. Now, notice this. These aren't the exact same as what we just saw, but they're still pretty similar to what we saw before. Now, what I'm showing here is the more these data sets that we collected are normal, the more that if I randomly make a normal set from their mean and standard deviation, they're going to look like them. If I were to have a distribution here that is not normal, so if I were to have something that looked like this, so this is called a bimodal distribution. If I were to have a data set that looked like this, and then I tried to do a random normal, it won't look the same. In fact, let me see. I don't know if this will work, but we're going to try it. See if they have one. No, they don't. But yeah, I can do this as many times as I want, and it's going to look similar. How do I know that? Because I believe with strong confidence that this is a normal distribution, both of them. All right. So I've made random normal distribution, well, sets from our collected normal data sets. All right, and I've done it like 3 times now. Question, are they similar or not? That's the question. Anyone can answer. Except me. Well, I guess I can, but I won't. Even though I guess I already have. Are these series similar or not? You guys are saying yes. Okay, let me be more specific with the question. Are the 2 new series similar to each other or not? Yeah, they are not. They are the answers to question 4 are the same as the answers to question 3. Because we've generated these from our old sets. So they're going to have the same behavior relative to each other. All right. Now we're going to put them all together. Now, since this is one I ran earlier this morning, and this will be a good chance to see. In fact, well, never mind, it's not that important. This is going to change when I run it again because I've generated these two new sets. And let me think. There's an error. Yeah, it's down here. Okay. All right. There we go. Didn't really change that much. It just goes to show that the original ones are very normal. Okay, now what you can see here, on the left, you got set 1S, which is the blue, and set 1, which is the green. So everywhere that's like this turquoise, well, it's not turquoise, but a deeper green is the overlap. In fact, the fact that it's so hard to find points that don't overlap goes to show the set 1 is very normal. Just has a high, it just has a low variance. And over here, you can see the non-overlap points a little better. So I would say that the set 1 is more normal than set 2, but it's not really a big deal. But you can see them overlapped. So are the series set 1 and set 1S the same or different? How do they compare? Same question for set 2 and set 2S. You guys have already answered that question. And yeah, they're the same. They're very similar. They are similar in almost every way. Why is that? It's because they have the same standard deviation and mean. How do I know that? Because I picked them out. That's how I made the new sets. I said, keep the mean, keep the standard deviation, throw everything else away. Okay. I believe here is where the error is. Can somebody try to run this cell and tell me if you get an error? Okay, so set 1 and set 2 are not defined. The reason is that a variable was never set 1. The variable was never set. Wouldn't say it's a pun. Some kind of English structure. The fact that set verb and set noun. Ha 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 ha. Here's the fix. What you're trying to use is set. I don't know what I did there. What you're trying to use as set 1 is the series from your data set. So my data, set 1, make sure you capitalize it. Same thing here, set 2 is my data, set 2, make sure you capitalize it. Okay, so we got our box plots. Now, if we remember back to box plots, they're kind of weird. What are they? Well, there are 5 things shown in a box plot. And what I mean by that is each individual doohickey here is showing us 5 things. You've got the range, you've got the quartiles in here. You've also are shown the mean, and that's the, I forget what it's called. It's the 5 descriptive statistic thingy. It's not RQR, it's something else. I keep wanting to say 5 spice, but no, it's not 5 spice. But yeah, what is this telling us? Well, visually, I can't tell the difference. Which one's set 1 and which one's set 1S? I don't know. Without looking at the label, I couldn't tell. That just goes to show you how similar the two things are. And over here, you can see they're less similar, but they're still very close. Now, what I can do, and this will probably take a couple executions, it's not a big deal. I'm going to remake everything. Well, not everything. I'm going to remake the random ones. Okay, and we're going to see, hopefully, set 1S and set 2S are going to change a little bit. Okay, yeah, they did. Set 1 and set 1S are still very stinking close. Set 2S still, it was smaller. The range was smaller. Now, this isn't a question on the lab, but if you've been paying attention, you should still be able to get it. It seems to be the case that every time I randomize, the set 1S is really stinking close to set 1. But set 2S is still, it's close, but it's not as close to set 1. Why is that? Why is set 2S more wobbly than set 1? Yes, that's exactly correct. It has more variance. More chance for it to differ in values. That's exactly correct. Okay, so interpret the results of the box plot. It's kind of what we've been talking about for the last 5 minutes. Are set 2 collections different from set 1 collections? Collections. Not sure what that means. What I would assume that means are those. They are different. Kind of depends on what you're looking at here. They're different in that they've got a different range, but they're similar in the fact that the relationship between this one and this one is similar to the relationship between this one and this one. I'm more interested in this part of the question when I'm grading it than I am this part, so don't sweat it. Everything I've talked about in the previous 5 minutes of the last 6 minutes is what you need to put here. Okay, suppose we were comparing the means of the 4 collections. Are the mean values set 1 and set 2 far apart? How many set 1 standard deviations is the set 1 mean value from set 2? Ooh, that's a good question. Okay, so question is, do you guys understand what this is asking? And Parth, I'm pretty sure you do, so you can just sit there and look pretty. Do you guys understand what this is asking? How many set 1 standard deviations fit into that? Yeah, that's pretty much correct. Yeah, it's asking, take the standard deviation of set 1. How many of those? So that will be like a length, like that. It's not that, but it's a length. How many of these does it take to get from the mean value, which will be the orange, of set 1 to the mean value of set 2? That's the question. Well, we actually know these. Can someone tell me the mean value of set 1s? I suppose there's 2 ways to get it. You could actually do the describe on set 1s. But the reason I ask is because I used it from set 1. 48.3. Okay. What is the mean of set 1s? I'll go scroll it up because the point I was trying to get across is it's the same thing as set 1. So if you had told me the mean of set 1, which you did, that's the mean of set 1s. So the mean of set 1 is 48, and the mean of set 2 is did I ask the anyway 48 to 508. So I'll even just do it all here. 508.2 minus 48.6. All right, so I got to get 460. That's what I got to traverse. That's the distance between orange to orange. Now, the interval we're moving in is in standard deviations. Now, what's the standard deviation of set 1s? Well, it's the same standard deviation as set 1. So what we're going to say is I want to divide this by 15.861475. All right. So it'll take me 29 standard deviations to get from set 1 mean to set 2 mean. How about the converse? All right, somebody tell me what to type in here to get the converse. Interesting. I intentionally didn't state the converse. So if you don't know what the converse is, a very important lesson to learn is in a lecture or whatever, if you don't understand what the question is asking, you need to point that out. You need to say, hey, I don't understand what the question is asking. Just change the denominator of standard deviation. Yes, that's correct. The thing I thought was interesting is that the standard deviation of set 2 is pretty close to the mean of set 1. So 47.978391. Oops, put in a... All right, so it'll take me 9.5 standard deviations to get from this one to the other one. Neat. Okay. Visit this place. This is the Wikipedia article in Six Sigma. The site of set 1 and set 2 collections are far enough apart to be considered statistically, oops, yeah, I'm on the right one, different. Repeat with set 1 and set 1s. Okay, so the rest of the lab is basically revolving around what is statistically significant. That's the question. So when you see in the news or the paper or whatever that somebody says, according to a study, we found that this is different from this. What they aren't telling you is that the study, when they ran the test on it, is that there is a statistically significant difference between whatever they're comparing. That is a term of art. That is what that means, is that that phrase, statistically significant, has meaning. So when I say two things are different, it's relative to my what I mean by different. What I mean by different can be different than what you mean by different. But the term statistically significant, so it'll be in here, has meaning. In fact, hopefully this isn't something weird. Yeah, here's what it really is. I don't, either we haven't got to it yet, or it's just a lab that's been dropped. But take what I've got here. What this means is that I've got a test. Just consider it a black box. You don't know what it is. You don't care. You put in two things you're comparing, and it puts out a number. If that number is this or less, then we can consider it statistically significant. Now, where does this number come from? If you remember back to when I was talking about this distribution here, 95% of everything I'm talking about is 2 standard deviations away from the middle. So this is 2 standard deviations in each direction. So what we're basically saying is, if you, on any random chance, you're not going to get something in the outliers. That's my 4-minute explanation for basically this. But for what you have to do, go read around until you understand. And I wouldn't say understand on a deep level, but be able to answer this with confidence. Confidence interval. I'm just full of math jokes. Okay, let's take a look at the homework. We've got some data. We want to make a histogram, determine if there's evidence of difference in the strength between the two brains. Okay. So we need to have a script that gives the plot. What kind of plot was asked for? A histogram. Give your English explanation. My Spanish and my Japanese aren't good enough to read, so it has to be in English. That answers the questions asked. And any sources you used to explain. Hint, hint, wink, wink, nod. All right. Here's the skeleton frame for what you're going to want to do. And that's that. So, any questions, comments, concerns, or if you've got your own math jokes? I'll also accept Futurama references, Star Wars references. How did you fix the error again? Here we go. It was here. The box plot is asking for 4 series of data. Problem is that these were set 2 and set 1. And it's expecting basically these variables were never set. My data set 1 and 2. Basically, this just never happened. So you can either put what I'd put it here, and this should work now, or you can replace set 1 with this. Okie dokie then. Anything else? Well, it doesn't look like it. I'll have the morning office hours tomorrow and the tutoring thingy in the afternoon. And yeah, bunch of grading to do. I didn't really do any over the homework that was due last week. I hadn't gotten to it yet, so I'm gonna get working on that. Can't really think of anything else. So everybody have a nice Monday. Also, time change is not fun.